Hi, welcome to the Water Research Foundation webcast on the Project 5081, Guidance for Using Pipe Rigs to Inform Lead and Copper Corrosion Control Treatment Decisions. My name is Jian Zhang. I'm a Research Program Manager with the Foundation, and I will be moderating today's webcast.
Okay, looks like we might have lost Jan, but I'm going to go ahead and continue on with the housekeeping slide. Just want to remind everyone to submit your questions through the question box at any time. We will do a Q&A at the end of the presentations. Slides and recording of the webcast will be available at our website. You'll see the link here on the screen. You can download the slides now and access a link to the project page to the left of your screen there under Event Resources. And a certificate of completion will be automatically generated after the webcast. If you have any questions at all, please contact me, Michelle Suazo. You see my email here on the screen. And then we do have a quick survey at the end, if you wouldn't mind just staying on a couple minutes to fill that survey out. It just gives us some feedback as to how we can better improve on our webcast. So with that, I'm going to turn it over to Dave Cornwell. Dave?
Hey. Thanks, Michelle. Thanks, Jan, for all your help in the project. I hope you join us again. Thanks for everybody listening in today. I hope you find this presentation and mostly this manual useful to you as you may move forward with these types of studies. I want to introduce our team, which was a tremendous team that was assembled and worked really hard to get this done quickly, and also to work with knowing there was very little budget to try to accomplish this. A manual like this really hasn't been created since the early 1990s. There was a document many have referred to as the WRF loop guidance document that's been used for many, many years. But that was certainly a whole set of different circumstances then. So I'm David Cornwell with Cornwell Engineering Group, and our firm was the lead firm in putting this together, but really it was an effort from everyone. I want to thank Rebecca Slayball from Arcadis and their firm, and Rebecca and their staff kind of really kept us all organized and a SharePoint site and kept things rolling. And Rebecca's team headed up a lot of the videos that were done. Pierre Kwan from HDR that led one of our groups and helped with a lot of checklists. Carolyn Russell from Corolla that led the costing group and created a great online tool for help costing these issues. And Melinda Friedman from Confluence Engineering Group that headed up our drivers and worked on all our fact sheets and helped keep us all in line. And also our support with Alan Ropers from ASWA that completed an ASWA survey on their needs for pipe rig studies and practices. Vern Snowick, retired from the University of Illinois, that many of you all know is probably one of our renowned corrosion experts, provided review of the whole document. And our 17 utilities that participated with us and worked really hard to be very actively involved, as I'll show you in just a little bit. The manual itself is divided up into 6 chapters, as you can see here over to the left: the introduction, drivers, design, operations, data analysis, and cost. And several supporting documents were prepared out of this: case studies. Many of the 17 utilities prepared a very detailed case study, which is in the appendix of the document. The ASWA survey results, fact sheets, checklists, design diagrams, our code training for how to do statistical evaluations. As I mentioned, the interactive budgeting tool and the videos. All of these are available from links on the Water Research Foundation site for this particular matter. Our project approach was that each PI assumed a chapter with assistance from their staff. So everybody was given one of these chapters, and each PI led a team of volunteers of utilities, consultants, regulators, and academics in order to try to put this together. Each team held 3 workshops to develop the chapter content. And again, all of the utilities and and the experts participated in these chapters. There was a web meeting at the end, at the beginning. As I mentioned, we have produced the case studies and videos and checklists. The YouTube videos, there are 8 YouTube videos, I believe, that were put together here, and you can see some of the topics. all the way from pipe harvesting techniques and videos on that, pipe preservation, startups of rigs, rig with SCADA integration, a very neat kind of interesting how to filter your samples. So very useful interactive tools by the utilities put together for us. Our team reviewed and helped with them and put them together. They're all available with links on the WRF site. And then a costing tool, an Excel spreadsheet interactive costing tool to help you estimate the cost of your rig study is also available that Carolyn and her group put together. Just a little bit about what we cover and we do not cover. The scope of this guidance focuses on flow-through, harvested, or new material studies. The guidance does not focus on static tests. I'll show you a couple of those in just a second. So really we're talking about, as we see in the little box here, harvested pipes, but also sometimes new materials as appropriate, as you'll see in the document. And pilot scale is our main focus. By pilot scale, I mean rigs that are located at water plants or in the distribution system connected directly to the system's waters. And bench scale flow-through studies are also applicable to many of this document, but it's not the emphasis of the document. And of course, the design chapter especially does not apply, but much of the other ones do. I always kind of like to say we try not to call them loop studies, although we all fall into calling these loop studies. Loop studies came from the fact of the very early document in the 90s, and that AWRF document I talked about were actually loops, as you see a couple pictures here. And that's the way they were set up. Sometimes they were all copper. Sometimes they were copper with lead coupons inserted. Sometimes they were actually new lead pipe, which was purchased and put into a loop. So they were literally loops. Now we call them, or like to call them, pilot flow-through rigs, harvested pipe flow-through rigs, and because they aren't really loops anymore, but that term still seems to come around quite a bit. This is just a little diagram showing some of the tests that are available to you and what you can do. Harvested pipe study tests are really required under the LCRI or the LCRR if you fall into certain circumstances and have to do those. But there are several other kinds of tests available, bench solubility tests being some of the very simplest. Those are sometimes called coupons, but they've been refined quite a bit since old coupon studies. Those are still called for as screening studies and things like that. There's galvanic tests, there's fill and draws. Then you move up to a flow-through bench scale study, a recirculating pilot, and a flow-through pilot. Our emphasis, again, is on the flow-through pilot, but to some extent apply to some of the other flow-through situations. Just some pictures of some of these things. Those top four are all static tests. The one in the middle there with the tubes coming out the bottom, that's a sealed static test, which is free from headspace free. Some of the others are batch fill and draw. An iron pipe static test over to the right, an iron pipe flow through test down to the bottom. I always like to say, don't forget about your other pipes if you're making some distribution system changes. And then the bottom left two there, the one on the left is a typical rig that Pierre will talk about a little bit for a pilot system. And in the middle is a typical bench flow through rig. So I'm going to turn it over to Melinda Friedman now to talk about the drivers.
Thanks, Dave. So when we think about why we're doing pipe loop studies, we have to think about what we call the drivers of the study. And these are really going to be, what are your key objectives? This guidance manual is about trying to develop fit for purpose guidance. Certainly, we're all going to have different reasons and different drivers for doing the study. So first we have to ask ourselves, why are we doing the study? And then the second step is to summarize what we're calling the influencing factors. These are your sources of supply, their chemistry, hydraulics, system type, system size, all of those types of considerations, which are going to have a very big impact on the siting, the design, the operation, the cost, data analysis requirements. When we talk about drivers, we focus on 4 key drivers. One would be a regulatory trigger if you're actually triggered through the LCRR into doing a study. The other ones are more often voluntary, such as you're introducing a new source of supply. Now, it says up to the states. The states do have discretion to require a pipe rig study if you're introducing a new source based on the complexity or the types of changes. And we're going to talk through some of those changes that you should consider. Likewise, a treatment change, if you're making a significant treatment change at the plant, the state does have the discretion to require a pipe rig study. We'll talk about what might be significant there. But then there's also voluntary reassessment of existing corrosion control treatment. On the regulatory triggers, we wrote this manual before the LCRR, so you can see there's, whether you could be triggered in if you have lead service lines and you've exceeded an action level, then you're required to do a pipe loop study. But there was also this concept of a trigger level when we wrote the manual, and that no longer applies. In the LCRI, there's no longer a trigger level. So a regulatory trigger would be you've exceeded an action level and you have lead service lines. Likewise, in the voluntary reassessment, there was concept that you could be doing a voluntary reassessment if there's a trigger, but that no longer applies. So really, though, what we're seeing is a lot of the utilities and that we've done the case studies on here are in this voluntary reassessment category, especially considering their concern or their area of interest is under the LCRR, the new monitoring requirements that are going to require you to sample more lead service line homes. And at the 5th liter, they are proactively wanting to do a voluntary reassessment of corrosion control. So the manual talks through these types of drivers that you could consider for your system, which are most appropriate. With regard to the influencing factors, this is really where we introduce a lot of complexity into the appropriate or a fit for purpose study. We identify these key influencing factors across the top, and each one is discussed in the manual. It's the influencing factors that are really going to have the greatest impact on your design and operation and siting and the duration of your study. If you bring on a new source, you have to have access to that new chemistry. Maybe it's a seasonal operation that's going to impact the duration of the study. So it's all these types of things that are going to be very important in how you plan and site and design your study. The chapter discusses each of these. There's a few pages, few paragraphs on each of these individual topics. But today, I just want to take a little bit time to focus on some of the supply chemistry influencing factors, since that goes back to those drivers. Are the types of changes we're making big enough to potentially warrant a corrosion control study or a pipe rig? So the manual is not meant to be a treatise on corrosion control theory. We tried to keep things high level, make the chemistry approachable. There's certainly references to other manuals and research foundation studies that where we can get all the detailed information on corrosion theory. But here's an example of some of the information that you could be considering if you're thinking of a source change or a treatment change. We listed some of the key water quality parameters here. We have pH, DIC is dissolved inorganic carbon, orthophosphate, ORP is oxidation reduction potential, CSMR is chloride sulfate mass ratio, chlorine residual, and calcium. And we just sort of color-coded some of the mechanisms that would be associated with changes in these parameters. So the lightest whitish gray color, all those parameters are going to affect the solubility of the metal. How much of the metal in concentration could be solubilized into the water? Whereas the blue boxes, these parameters will impact the mineral, the type of corrosion scale that is formed, the mineral that is actually formed. And if you're going to be changing chemistry or sources, you'll want to understand whether the new changes or the new sources are compatible, or how you might be changing the mineralogy of the scales. And then the gray boxes are other very important corrosion mechanisms that should be considered, such as galvanic corrosion or microbial biofilm impacts, calcium precipitation that could impact water quality and water stability. So just high-level overviews of the parameters that you would want to be thinking about if a pipe rig or corrosion study is appropriate. Diving a little deeper into just the pH and DIC changes and their impacts on lead solubility, my colleague Verpi Salaziman with Confluence developed these graphics and the fact sheets I'm going to talk about. What we're trying to show here are what we consider sort of safe, warning, and danger zones. So if your combination of pH and dissolved inorganic carbon is in the green zone, and you are introducing or making a change that's going to keep you in the green zone, we would consider you probably safe. That's your lowest lead solubility zone. And then the yellow zone is sort of medium lead solubility, and the orange is the high lead solubility. So if your current sources, if you're not doing corrosion control treatment and your current sources are in the orange zone, and or you're going to be introducing a source or making a change that puts you in the orange zone, you are most definitely going to need corrosion control treatment. That should just be an assumption that you should plan into the design of the new source or the treatment. If you're introducing a source or a treatment that causes shift from green to yellow, it certainly warrants a corrosion control study, but maybe or maybe not a pipe rig. So what we want to consider is, are we having significant changes in these key water quality parameters, but also are those changes going to be implemented in a geographic area of the distribution system that has lead service lines, copper lead solver, a lot of old galvanized pipe. You know, if you're bringing on a new source and it's a very new area of the distribution system and there is no, after all the lead bans, there's no lead solder, then maybe a pipe rig isn't needed, but certainly a corrosion study is. So it's putting all the pieces together to help states understand if and when a pipe rig study is appropriate. The manual provides also a summary of the treatment changes and those impacts on these important corrosion-related water quality parameters. So down the left side in the column, there's a whole list of treatment changes, and this information was compiled from other AWWA manuals and Water Research Foundation projects. And then across the columns are the potential, whether those treatment changes have impacts on the various potential important parameters. And I just want to highlight quickly the implementation of anion exchange with the new hexavalent chromium rule in California, and a lot of concern about PFAS and, of course, arsenic. If people are adding anion exchange, just to be aware of things such as you might be adding chloride to the water while removing the sulfate, and of course that can impact the CSMR and galvanic corrosion. So just a matrix for you to think through how your treatment changes may impact important corrosion control parameters. I mentioned, and Dave mentioned, that a series of fact sheets were prepared that, in this example here is just for pH, quickly summarizing impacts on solubility, impacts on scale type, again, the minerals that would form, and then examples of types of changes that could be danger, warning, or safe zones. So again, you can do much more research and other manuals to get more information, but these are just quick, nice overviews to help understand the need for pipe rigs. And these types of fact sheets were prepared for pH, orthophosphate, temperature, DIC, and alkalinity, trying to discuss some of the changes that might implement a safe warning or danger zone. And finally, I just wanted to give a shout out for the case studies. 11 utilities provided detailed case studies, and we had a variety of conditions. They describe what type of treatment they have, what their driver was for doing their study, and what their key influencing factors were. So hopefully, if you are embarking on this road, you can find a utility that's got somewhat similar situation and see what they did, what worked for them, what didn't work, and where they are in their study. So for example, the Massachusetts Water Resources Authority is doing a voluntary reassessment. They are a wholesale supplier, but some of their wholesale customers that have lead service lines have been experiencing action level exceedances, and with the concern of going to fifth leader, they just want to make sure that they are in good shape to voluntarily optimize, ahead of any of the regulation coming out. Likewise, Tacoma Water did a nice case study looking at impacts of alternating between surface water and groundwater, and trying to understand the need to which their groundwater might require treatment. This case study is of interest because this is in the Pacific Northwest. We have very few lead service lines. Tacoma Water did not have any lead service lines. They did have some goosenecks, but they also focused on other materials that might be of interest to some utilities in different parts of the country. Aqua Water Utility Services did a very big source water change. They changed from a groundwater with sequestration to a surface water with softening and conventional filtration. So there's a interesting case study on what to prepare for. What kind of study did they do to try to predict impacts of this big source water change on metals release? And then finally, City of Toronto had installed sentinel loops in their distribution system that they're using as an ongoing sort of indicator of corrosion control conditions out in the distribution system. Great Lakes Water Authority also has, and we did work on case studies with them too, had their rigs at treatment plants and in distribution systems to try to understand some of the impacts of what's going on in the system. So in summary, water systems may need to conduct pipe rig studies under the LCRR, and that could be due to a regulatory trigger, a source change, a treatment change, or you may voluntarily just want to re-optimize. It's been decades since folks have maybe looked at their corrosion control water quality parameters, and with the changing regulations, wanting to get ahead of the regs. Clearly defining your study drivers is critical to study success and ultimately approval from the regulatory agencies. And then a clear understanding of influencing factors is needed for proper siting, design, and operations to meet your study objectives. So I will now turn over Pierre to go into more detail on the design considerations.
Great. Well, thank you, Melinda. Based off what Melinda's just talked about, the drivers, we now will go through, once a pipe rig has been identified as being needed for your study, very first step is the design. We want to start off with, where do these things go? How are they implemented? And so I had the pleasure of working on this team to lead the design chapter. And really it's helping water systems, figure out, okay, what type of rigs are needed, the materials, where it goes in, as well as allocating all the needed space and materials to make this a successful effort. The parts of a successful pipe rig design really fell into 4 main categories, and I'll talk about the first 3, which is the location, where do you put these in, water supply and disposal, and their implications on that, and then water quality adjustment. This is especially important for those systems who are looking to change pH, alkalinity, or phosphate, orthophosphate doses. The last one, which was the utilities had indicated in the study, was really key to making a pipe rig study successful, was the test pipe. I won't talk too much about that. That will be in the operations section led by Rebecca, who will be after me. So let's start off with a location. These systems are actually quite big. We need space for the pipe rig itself. And I'll show in the photos throughout my section area, highlights the size of these things. But in some cases, if we don't have available footprint, usually horizontal footprint, we can go vertical. And this is a photo from Tacoma Water, where due to footprint restrictions, this pipe rig was built vertically. But we also need area for the work tables and chairs for the staff, benchtop analytical equipment, such as the pH analyzers or Hawk test kits. If we're doing right at the rig, both filtration for both total and dissolved analysis, we want to have that space for that, especially for systems doing pH, alkalinity, or phosphate adjustments. We need area for those chemical feed systems. And then since we're doing chemical feed, we also have to allocate space for the required safety equipment. The other consideration as relates to water or to location is water supply and the floor drains. We're bringing a lot of water in, we'll be using it, and then we have to dispose of it. Other aspects of that location that we need to consider is away from vibration, especially large mechanical equipment. Most pipe rigs are located at treatment plants, which happens to be also the same location as large backwash blowers, compressors, backwash feed pumps, high service feed pumps. Having a rig too close to large equipment can induce vibration through the concrete that comes up into the pipe rig, and therefore producing artificially high particulate lead results. We also want to have these rigs away from normal foot and equipment traffic, as well as with good lighting, because especially those systems using chemicals, it just provides a better, safer work environment. One aspect that was mentioned was climate control, especially EPCOR up in Alberta. They purposely set their test rig in a very cold room to simulate the Albertan winter conditions. Now that is a unique feature that they did, but that could also be applicable to test rigs in other locations like the American Southwest, where it gets extremely hot during the summer. So climate is a good consideration. Water supply and disposal, again, commonly installed at water plants because we have a lot of water and a lot of sewer service. However, the utilities in the study did note that it isn't necessarily the most representative water distribution conditions where the corrosion is actually occurring. Water could be warmer, out in distribution, lower chlorine residuals, as well as potential for nitrification. Dave mentioned at the beginning that this study was specifically about flow through pipe rigs. We want to be, the guidance is for around fresh water. This water quality is generally stable. It allows for a less complex system and easier to analyze data. A photo here is actually from Aqua America's units in Pennsylvania. Going from left to right, you see there's a workspace with chair and table for the operators to log data, measure stuff. In the far back is the chemical feed system, and in the far on the right is the pipes rigs themselves. Recircling pipe rigs. Now, as Dave mentioned, that isn't the emphasis of the study, but for the design chapter, we do talk about it for a bit because it is a type of rig that is used for corrosion studies. Does not use as much water as flow throughs, but they're really difficult to use and really should be used only when you're getting water from a pilot test where water supply is already limited, or water needs to be hauled to the test site because there's no available water supply, as well as no or limited sewers. There are a lot of downfalls with this type of rig. It's much more mechanically complex because you are recirculating the water, a higher potential for microbial impacts because of that recirculation, and because the water's used over and over again, data analysis does become more difficult. So example test pipe configurations. A lot of utilities provide photos of what they installed, and wow, they're all different. Starting from the upper left, for their specific needs, New York City's DEP, in a pipe corridor, utilidor, they literally took their pipe, harvested lead pipes, strapped them to the wall. Bottom left-hand corner, Toronto Water, they're pretty innovative. They had very long service lines. They put them in use intact and actually used ladders, aluminum ladders, as a structural support for all their pipes. Whereas in the upper right-hand corner, this is the pipe rigs used in Flint, Michigan. They cut the service lines into segments to put them in a serpentine path through those rigs. They're also up on wheels, so these rigs could be moved around between different locations for use. Whereas in the bottom right, Great Lakes Water Authority had large rigs that were then permanently mounted, bolted to the floor for their use. A key consideration for the design of pipe rigs is the chemical systems. And this is actually a uniform comment by the utility saying that this is probably the hardest part of the test rig because chemical use is so low, easily in fractions of a mil per hour, and therefore need to be highly precise feed systems that require the controls, interlocks with the pipe rig so that we are getting the correct chemical use through the system. And we are using a lot of chemicals sometimes, phosphoric acids, orthophosphates, sulfuric acids, sodium hypochlorite, hydroxides, and so forth. Besides the controls and the installation of the systems, a lot of consideration needs to be considered for the health and safety requirements, both for equipment and footprint. So in the design chapter, it laid out a lot of different rigs that the utilities used. And we tried to collate everything together and synthesize this to information that the audience can use at their respective locations. We prepared a location selection checklist indicating everything that you need to look for before putting one of these in. General pipe rig equipment checklist that you could then use to start ordering materials, a parts list for actual fabrication. Emphasis is, again, chemical flow rate calculations. Again, because chemicals are such a key part of the system and their flow rates are so low, we provided calculations to make sure you go through those steps properly. And then a lot of example process schematics so that you could use them as different templates for your specific site conditions. So in summary, we found that of all the participants, pipe rigs can be quite complex, and a lot of thought needs to be put into the design and implementation of them before going to like harvesting pipe or start using these things. Key issue was none of the 17 utilities use the exact same type of pipe rig. They're all custom because of their site specific distribution system configuration, space and location constraints, as well as the specific test requirements, both in materials as well as in chemicals. So all that's been synthesized in the design chapter. Now I am going to pass this off to Rebecca, who talks about the operations once a system has put these in.
Thank you, Pierre. So moving into operations, this is the most resource-intensive phase of the study, both from a human labor as well as a cost perspective, and requires meticulous planning and execution to ensure the study conditions are met and representative, and that useful data are collected to inform the necessary treatment decisions. So operations generally consists of 3 phases. The first is the pre-startup phase. Here we want to confirm the operational integrity of the rig and obtain and install those representative test pieces, which could include harvested test pieces like lead service lines, lead goosenecks, as Melinda mentioned, galvanized pipe as well, or other materials like iron or other mains in the distribution system that might want to be analyzed as well. It could also include new materials, including piping like copper or copper with lead solder. There are also then the acclimation and testing phases. This is where the bulk of the operations are going to be performed, where we are actually exposing the test pieces to water during this time. So during acclimation, all the test pieces are exposed to the same water, typically existing water conditions. And then during the testing phase, we're going to switch a subset of those test pieces over to the alternative water quality conditions, such as an alternative corrosion inhibitor or an alternative corrosion control inhibitor dose during that testing phase. During both acclimation and testing, we're going to be collecting different types of water quality samples, which we'll talk about, and performing maintenance on the rig and test pieces as well. The other piece that's really important to the acclimation phase is using that data to determine stabilization, which Michael will be talking about in the next segment. And then in the testing phase, that's typically one where then again implementing and operating those chemical feed systems that Pierre just talked about in terms of the design and challenges from an operational perspective. So one of the steps in the pre-startup phase that I wanted to highlight is harvesting and preservation of different service line materials. If this is not performed properly, it could impact the duration of the acclimation phase and the overall data and interpretation of those results, as well as the overall study. So it's really important to spend time thinking about and making sure you've got proper procedures for harvesting and preserving these materials. In terms of harvesting, we want to capture materials from regularly used sites that are representative of typical water quality conditions. So ideally, we don't want to harvest from locations like abandoned properties where water has not been regularly used and flowing through the service line. In addition, if you have different water sources throughout your system, you may want to capture lines from those different areas that are served by each source, as there could be differences among the scales on those pipes, which might be important to understand and test during your study. However, we do want to recognize that harvesting can sometimes be limited and restricted to locations where ongoing replacements may be occurring. So if you have an opportunity to do that, you may still want to try to distribute them throughout different replacement locations across your system. We want to make sure we're using an open trench method to minimize any damage to the pipe and interior scales. And if you are going to be planning for scale analysis, either before or during your study, be sure to account for that when determining the appropriate length of pipe that is needed for your study. Typically, you need about 10 extra inches for each scale analysis that you're going to be performing. We generally recommend that after harvesting, you install these pieces on a rig with flowing water within 7 days. However, that's not always possible. So alternatively, you can preserve these for significant periods of time. We recommend putting damp sponges in the end and checking the pipes at least monthly, if not weekly, to try to confirm that the scales have not dried out, and if needed, re-wet the interior scales. I do just want to note that there are videos available online to illustrate both the harvesting and preservation process. And I also wanted to just spend a minute talking about new materials, which can also take a long time to stabilize as they develop those initial passivating scales when they're first exposed to water. So one thing that you might consider for new materials, which can be impacted by things like workmanship or the manufacturing process, is exposing those test pieces to a water source, either the one that you're going to be exposing them to during the acclimation phase or an NSF extraction water, and actually measuring lead and copper from the water that's been exposed to those test pieces and remove any outliers ahead of time, as those could, again, significantly impact your results or interpretation of those results in this study. So as we plan for activities during the acclimation and testing phases, you'll want to think about things like the rig pressure and flow, operating schedule, water quality monitoring, and chemical feed system maintenance, each of which I'll cover in a little more detail in the next few slides. Here, I just want to note one important observation around the duration of both the acclimation and testing phases. As you can see from the table on the right, these can vary and are influenced by the goals and objectives of the study, in addition to things like budget, staff availability, and the collection of actual data for sampling from the individual pipes. But most commonly, acclimation phase typically is around 6 months with another 12 months for testing. So 18 months of just solid operations is a good planning estimate for folks as you're thinking about preparing your studies. I do want to note that some systems have continued to operate their rigs and do after the study, either to evaluate other water quality or operational changes or to use as early warning indicators of increased lead or copper release as well. So the pipe rig should be operated in a manner that's consistent with residential water use or mimics that residential water use. That would include typical pressures and flows. And we note some suggested recommendations for those ranges on the right-hand side of this slide. In terms of the schedule, as is in a typical home, you have different periods where water is flowing through the service line and interior plumbing, and periods where water is not being used. And we want to try to mimic those in the operation or schedule of the pipe rig. So the number of periods can range. We saw anywhere between 1 and 6 in the case studies that were documented, with 2 or 3 most common, and typically having at least one longer stagnation period of 6 hours where you can then capture water quality samples from those individual test pieces, which I'll talk about coming up. This slide here shows some examples of those flow and stagnation schedules. The colored bars represent the time when water is flowing in the rig over a 24-hour period. And as you can see, there's lots of differences in terms of the number of flow periods, the duration of those flow periods, and when they're actually occurring in a 24-hour period. This just, again, re-emphasizes the idea that there are various operating schedules that can be implemented, and they should be tailored to your water system based on factors like access to the site, staff working hours, sampling schedules, and even drainage if there are restrictions around drainage in your test study. Also want to note that increased stagnation may be necessary if you have very low or non-detect levels of lead and copper across all your test pieces. If that is the case, you're not going to be able to actually see any differences in the alternative conditions you're testing. And therefore, you may want to increase the stagnation to get a signal for lead or copper during your test. So moving on to water quality monitoring, there are various components that will influence the development of a water quality monitoring plan, including things like sample type, location, frequency. I'm just going to spend a few minutes talking about the first one, which is sample type. So there are two types of samples. The first are flowing samples. These are collected typically 5 to 10 minutes after water has been flowing in the rig, generally from the influent to that rig to characterize the water quality, or after chemical addition to verify the water quality parameter targets that you're trying to achieve are actually being achieved consistently throughout the duration of the test. The second type is stagnant samples. These are typically collected from each individual pipe effluent to characterize metals released from each test piece. You here would want to consider using a protocol that is consistent with regulatory requirements where the driver is regulatory based. If that's not the case, you may again want to try to target at least 8 hours of stagnation to mimic typical stagnation in a home when folks are sleeping and water's not being used. And really then to capture detectable metals again to help make more informed decisions. This slide here just lists a few other best practices for sample collection and analysis. So depending upon the design of the rig, which as you saw from Pierre, can vary significantly, systems do need to be aware that there may be a volume of water in contact with non-metallic piping or tubing between your test piece and the actual sample tap. And you just need to understand that and either account for it or adjust for it when you are collecting your individual samples from each effluent test piece. Second, we want to maximize the use of wide mouth bottles to make sure that we're capturing that entire sample volume. Sometimes it can spray out a bit from the sample taps. So to the extent wide mouth bottles can be used, those are recommended. And then if you're going to be filtering samples, 3 things to keep in mind. 1, try to perform that filtering immediately, but no later than 24 hours to reduce any metals that might adhere to the actual sample bottle. We also recommend avoiding the use of polypropylene media. It's really hard to just push the water sample through that specific filter. And then note that colloidal present particles may still pass through the filter and they might be present in that filtered sample. So the sample is not necessarily just dissolved or soluble concentrations that you're measuring. Colloidal particles may still be present depending upon your specific water quality and scales that are present. Also a reminder here that there are, again, videos available to capture some of these best practices around sample collection and analysis. In terms of chemical system maintenance, there's a table here that captures many of the common activities and recommended minimum frequencies, but these are obviously going to depend upon the design of the system and the specific equipment that was selected. So maybe just a couple tips to keep in mind when you're going to be putting together your rig. Consider pumping non-chemically treated water, so either source or tap water with no chemicals, to the rig to confirm the target flow rates are being achieved. And then at the start of the testing period, or when you're going to actually get moving with chemical addition, if it's required, consider gradually increasing that pump flow to avoid any accidental overdoses. In addition to all those case studies that were captured as part of this report, we had a lot of great lessons learned shared. Many of them are listed here on this slide, as well as in those detailed case studies that Melinda talked about. I just want to highlight the first one. So in many cases, we see a lot of variability between replicates or test conditions, particularly where harvested materials are used. The figure on the right shows the acclimation phase and the lead concentrations that were measured in the individual pipe segments during the acclimation phase. And you can see they're all over the place. You know, some are high, some kind of bounce around, and we didn't see good stability happening. So here we actually ended up implementing higher flow periods. We increased the flow to about 2 to 3 gallons per minute for about 30 minutes per day for about a week to try to remove any loose particles in there and reduce that variability. You can see there were some spikes afterwards, right after that flushing happened, which is the black vertical line, but then actually all of the test pieces did settle down and we were able to see good stability before moving into the testing phase. So to summarize operations, there is no single approach. Similar to design, it's very system specific. You need to, also think about operations very diligently when you're designing your pipe rig study, and think about things like staff availability, site access, the number of sites, the number of test materials, your lab turnaround time, and budget as you're coming up with your operations plan. But at a minimum, I would recommend planning for 18 months for acclimation and testing. That's, again, on average, what we tend to see for the operations phase, but be ready to adjust to changing conditions in the field to make sure you've got enough time and staff to support this important phase of work. And with that, I'm going to turn it over to Michael, who's going to talk about looking at this data and making some informed decisions.
Thanks, Rebecca. All right, so I'm going to talk a little bit about what's offered in the data analysis chapter. And we've already mentioned actually a few different areas of data analysis as we've gone along through these previous chapters. In the driver section, of course, we talk a little bit about how the various water quality parameters might impact your lead levels and your corrosion levels. And in the operations chapter, of course, we went into discussion a little bit about stabilization, as well as, of course, all the various water quality parameters you might want to keep track of. Data analysis chapter specifically is going to cover the visuals and statistical tools that are used for these 3 different areas of the analytical process. The first is routine monitoring. Of course, we've already went into that in the operations chapter. The second, again, brought up in the operation chapter, a very critical aspect of how long your study will last, and as well as getting good data for your comparisons later on. We have stabilization, and then finally we have treatment comparisons. And it seems like I forgot my camera on. Appreciate it. And finally, we get treatment comparisons in which we actually there find how our different corrosion control treatments that we're testing, if one is performing better than the other, if you're testing replicates, how do they compare with each other, so that you can see consistency or slight differences in your system. So I'm going to start first, of course, with the routine monitoring. Of course, we've already covered this a little bit in depth, but it should be considered when starting up with operations, starting your pipe rig study, that you have a good graphical and statistical tool that you can use to store and then process the data that you are collecting from your pipe rig experiment. So there's a couple that we've used effectively in the past. Excel is a very good visual tool, and it has a very good user interface, though it lacks some statistical capabilities that a program such as R is very good at. And of course, sometimes you may want to set up your programs to try to run both, or maybe you want to use the two programs separately, depending on what one is better at doing than the other. But these should be considered prior to the study, so that when you actually go ahead and start monitoring data and collecting it and looking over it after a period of time, that you can make adjustments if, say, something occurs later in the study that you want to look more into, or if you want to get a quick look at what your lead data is looking like, things like that. It's just an example setup we have here. If you were to create an input form, for instance, that you give to your operators and that they write down the water quality parameters that they're monitoring, you can have this linked to a database. This is one to set up in Excel, and then you can have all those different columns to create graphs automatically, so that you can just go in, take a look at the graphs, see how the water quality parameters are, how they're looking like. If they're at the target levels, are they changing due to the different changes in seasons, things like that. Of course, this is talked about a little bit in the data analysis chapter, not these particular images, but I did want to show an example of how this might be set up. I'm now going to move on to the more interesting aspect of data analysis, and that's stabilization. And stabilization is probably the most intensive part of the analytical process, as it occurs alongside the water quality parameters throughout the course of the rig monitoring. But there's a lot more analytical details that need to be covered when analyzing stabilization. So in the document, we describe stabilization as when pipe lead levels achieve steady state with the applied water conditions. What this means physically is what we're trying to determine is when the pipe scales have adapted to the CCT test conditions. And this is important when we actually go about comparing the different CCTs, because we really want to see at their lowest stable lead level, that they're consistent lead levels, that is. We want to see what those lead levels are, and if they're showing consistently, then we have the stables have been shown to be developed in that case, and we can go ahead and start making treatment comparisons. For the analysts, of course, I've been sort of alluding to this, talking about how this physically is being represented, but this needs to be this is generally shown with a horizontal slope and a tight spread of data. So if the data is too spiky, as you could probably see, like in the middle of that graph there for that blue line, that might the pipes might not be quite yet stable, even though I could draw a horizontal trend. If obviously not that many points there to work with, but it needs to not show that the lead levels are going all over the place. I'm going to go through a little bit of example of how this analytical process works. So for instance, I just took one of the pipes that I show on the graph, and the graph is, of course, in the chapter. And this graph is just all of the little data points that make up that line graph that we saw before. I would then look at this graph, and as I'm collecting data, I would grab the most recent set of data points. I would try to aim for around 10 samples minimum. I'd obviously want more to increase power, but let's just say, for instance, that I took the samples here on the right-hand side of the screen, and I thought that this would this area would indicate that the pipes are stable. I would then go ahead and check that by using statistics. And if I go to the next slide here, I list a couple of various different ways you can go about doing that using the statistical procedures that I mentioned in the chapter. The first one is correlation testing. All that is essentially testing to see if there is a zero correlation. Zero correlation indicates two things generally. The first thing is important to us. We want to see that a zero slope occurs, and having no correlation in the data would indicate that there is neither a positive nor a negative slope that the samples are trending. Of course, this also can indicate that there is absolutely no trend at all in the pipe, and the dots are spiked everywhere. So this is something that if you can easily confirm with the visual. So if the visual indicates that it looks like there's an actual trend occurring, then the zero trend would indicate that there is a zero slope there. Confidence bounds is another interesting one, as unlike the correlation testing, which gives you an actual value, you can use with a hypothesis test. Confidence bounds are actually something you can plot onto a graph, which are a visual indication of slope. If I were to draw these two confidence bounds that you see here on the left-hand side of the screen on the graph, this is indicated by the two black dotted curves. If I were to draw a horizontal line in between those two dotted curves, I could then indicate, that would indicate to me that statistically we have a zero slope. Of course, this requires a visual assessment to do. You could theoretically just use use the values and make a value line between those curves, but this is a very quick method to do using a graph. And then finally, a goodness of fit test is also mentioned. This is a type of test that we could use to test for data tightness. Again, this is great to use alongside visuals, as goodness of fit testing can sometimes be a little bit strict, which is good, but it can sometimes give some awkward results, if you would, but it is usually pretty effective at testing for data tightness. All of these tests that I just mentioned, as I've been trying to emphasize, work very well in association with visual graphs, which I'll show a bit later. And that's something that I think every analytical process should incorporate, is even though numbers are great, and there definitely should be numerical values associated with determining stability, but that doesn't mean that the visuals can't tell us nothing. These are definitely helpful, especially in making the stabilization process of grabbing points very quick, because as we started out, when I started out doing all these tests, showing you this example, I had to take these grab these 10 samples from a visual inspection. And of course, if these 10 sample points failed at statistical inspection, you'd have to either wait for additional data points to be taken, or you'd have to go and grab a new set of or additional set of points to see if stability has been achieved. So this can be a very tedious process, but that is very helpful using both the visuals and the statistical methods. I'm going to finally get on to the analyzing the results. And once we've actually analyzed these, grabbed these statistical results, these stable results from analyzing stability, we can then go ahead and compare those different results using a variety of different methods of visuals and statistical methods. I don't list the statistical methods, but for example, you can use things like a Mann-Whitney test and a Wilcoxon rank sum test. Sometimes you can use ANOVA testing to make those various different comparisons. But there's two main types of comparisons that generally occur when we're analyzing results in this way. The first, of course, are between replicates, and once you have two pipes that have the same control treatment being tested, and you want to see how those different pipes can compare against one another to see any distinct differences or similarities between different locations and addresses, or even different sections of pipe from the same address. Same thing with the testing different CCTs. These can be evaluated for effectiveness depending on whether or not you're doing an ortho-dose change, or say even a pH versus an ortho treatment. And I also want to emphasize too that even though we are using just stable results, all the data used beforehand is also accounted for when we get into things like implementation plans, and also just quality control of the rigs, things of that nature. I'm going to get into real quick into the just how a statistical comparison might look like. Say for this example, we have all these 5 pipes, and each of them is a different phosphate dose. I can obviously look at this box plot, and that would be very effective at showing, hey, this 4 dose is actually showing the best results. These did have statistics run on them, and I kind of used the arrows to indicate how the statistics panned out, and these were used by a Mann-Whitney test. And as you can see, there's very slight decrease from the 2 to the 3 dose, but we see a drastic increase and a statistical bell, if you would, that indicated that the 4 dose versus the 3.5 did a very good job in showing low lab levels. I'm going to move on to my last slide, and just to show, besides the box and whisker plots, there's a lot of other different ways you can show your data, such as with a dot plot. This has been used effectively in the past before, and that kind of would indicate show you actually all the different samples that are incorporated into that box and whisker plot, which you might not be able to see. And things have also from back in the stabilization and the routine monitoring. I'll make a quick note on the second row there with the histograms and the quantile chart. You really want to optimize your rig study. You can incorporate normality tests, and normality tests can allow you to use a variety of statistical tests that may increase the power of your results in the study. I'm now going to pass it on to Caroline, where she's going to actually go and talk about the cost of the various of a rig study, and as well as the cost of program that we developed as part of the project.
Thanks, Michael. So for this portion of the project, our objectives were to identify factors influencing costs for pipe rig testing, and to develop a cost tool that provides planning level estimates for a range of testing approaches based on user supplied information. Just double checking, does my camera show up?
Yes.
Okay, perfect. So if you look at the graph on the right, I want to highlight a couple of things. You can see that for each of the different cost components for pipe rig testing, the cost can range a lot from system to system. This is an illustration of the range of costs that we identified from a literature review, from our team experience in the participating utilities in the case studies. And as an example, for pipe rig operation, even normalizing on an annual cost basis, there's a big range in costs that can be incurred. And that can reflect things like if you're conducting a pipe rig at multiple locations, if the location's far away from the home office and you have to drive a while, if you're how many replicates you're collecting samples from. For pipe rig construction, the cost can vary a lot depending on whether or not you need a new shelter or if you need new electrical versus whether or not those requirements are already in place at your pipe rig's test location. So as part of the project, we developed multimedia guidance. In the report for the WRF project, we have this table shown at the right that lists out budget planning questions that utilities can go through at the onset of their study to kind of think through how they want to do the pipe rig testing and those questions specifically relate to how much the pipe rig study might cost. We, in the report, go through a summary of factors influencing costs, and we give examples based on the case studies of the ranges of costs that can be incurred for different line items. In the cost tool, we have, I'll talk more about this, we've estimated staff hours to complete pipe rig study components in-house. So if a utility is doing the design of the pipe rig study, doing the construction, doing the operation, we've listed out estimated costs for utility staff to do that work. In the cost tool, we also have compile costs for the components required for pipe rig testing. So if you're embarking on a pipe rig study and you want to know how much is a pump going to cost, or how much is it going to cost to harvest lead service lines for pipe rig testing, there's all of that's documented in the cost tool as a resource. And then the cost tool itself is a tool to be able to estimate the cost for doing a pipe rig study. You can also do scenario planning as well with it. And this is just a home page for the cost tool. I'll go into that a little more. So yeah, this is the home page again. So the cost tool, when you open it up, you can download it from the WRF website, and it has 8 different tabs. The first tab is a cover tab, and it allows you to link to the default cost calculation in blue, or an advanced version of the cost calculation that you might use if you know a lot more about what your study is going to look like. There's the default cost calculation tab, which I'll go through more. For the advanced cost calculation, you'll start at the input tab where you'll enter in the site-specific factors that are going to influence the cost. You can go to the output summary tab for overall cost of the pipe rig study based on the estimate and some summary details. And the advanced calculation tab gives you the actual line item costs for individual components like the shelter, electrical, and you can also see how those costs were tabulated. The library of costs includes unit costs for each component of pipe rig testing. And then the cost basis tab is where we put in all the information that we gathered from the case studies, the literature, the project team. So for harvesting pipes, for example, you might see multiple line items that reflect the cost for multiple studies, and you can get a kind of sense of the range and also see some site-specific cost values. And then finally, there's a reference tab. In terms of how the cost tool works, this tab on the cost basis, you can see where we've entered in line item costs for multiple different case studies for different components, like the cost of design and planning, the cost of harvesting pipes, the cost of new pipes. And then those costs are used to compute unit costs for a specific line item. So for harvested pipe segments, for example, that weren't harvested as part of a lead service line replacement, what we've done is we've taken the median value of the range of values that we were able to obtain through the case study examples and our team experience in the literature. And then those unit costs are called upon when you go into either the default cost tab or the advanced cost tab. You enter in your site-specific pipe rig test characteristics in the orange shaded cells. And then in the green, the output on the costs are provided. And those green calculated costs are based on the input values and calling on the unit cost for different components. For example, if you know that you're going to have 3 replicates per condition, you enter all this data in and it has 18 segments, then the calculation is based on 18 segments times the unit cost for a harvested pipe segment, for example. So now I'm going to go into a couple examples of how you can use the cost tool. What I'm showing here is the screenshot of the default cost calculation. I want to point out a couple of things. If you look at kind of at the top of the very top orange cell, you can see the year the study will commence. And so what we've done is the costs that were built into the model are based on 2022 costs. And we've added an escalation factor to be able to adjust to current dollar values based on an interest rate so that this model stays current. And you can actually go in and change those escalation rates if you needed to. So then in this particular case study, what we're indicating is for a study that would have 2 corrosion control treatment conditions they wanted to test, including a control. So the 2 corrosion control treatment tested in parallel with the control, 3 replicates per condition, 1 type of material to be tested. In this case is a copper pipe with lead solder that's been harvested from homes constructed pre-1986, and 1 source water condition. And for this case study, the contractor is doing all the work, the design and planning, pipe rig construction, operation, et cetera. And then we've also entered in the duration. And what you can see is then an estimated cost of a little over $500,000. And on the right, you can see where the breakdown is of those, that $500,000 in terms of cost components. And so maybe you have a budget and you're trying to think about how can I do this a little bit less expensively. You can play around with this default cost tool to see, where can I cut costs and still achieve my project objectives. So in the next slide, I'm going to show how these costs change if, for example, maybe the utility of under consideration has 2 different surface water treatment plants and they want to run a pipe rig looking at their ways to optimize corrosion control treatment at each individual surface water treatment plant because they have different finished water quality. And so what I'm going to show is that the number of sites per testing, or the source water conditions, I'm going to increase that to 2, or actually increase the number of sites for testing for 2. So we're doing one source water condition per each site, each of 2 different surface water treatment plants. And I'm going to go back and then I'm going to go forward again. Pay attention to the red cost at the bottom and the graph on the right. You'll see that the total cost of the pipe rig study increases almost 2-fold. And the operations cost is one of the line items that really increases a lot because you're sending staff out to operate 2 different pipe rigs. So the last, if we move forward, I want to talk a little bit about how these, how the pipe rigs are completed, whether or not it's using in-house utility staff or a contractor. In this example, what we're showing is a contractor doing all the work, but there's still some level of effort from a utility to be in meetings, to participate in decisions, to meet contractor staff out on the site. And in the cost tool, if you'll scroll down to the bottom, you can see where those estimated hours are and total hours for the duration of the project for utility staff. And utility can use this information to make a decision on whether or not they have the resources they need to do the work. And maybe they decide that they need, so they can include that in terms of resource planning. So this is staffing with outside contractors. But if we decide instead that some of the work the utility staff can conduct themselves, the utility has the resources available, maybe the utility is going to do the design and planning, and they're going to do operation, data analysis, and reporting. And what happens is the red bold cost at the bottom goes down because this isn't cost that's going out of the utility to a contractor, but there is a cost incurred in terms of utility staff hours, and those go up and are reflected in the table that's in the cost tool. So the last thing I want to talk about in terms of the cost tool is for the advanced tab. And what you can do if you know more about how you're going to conduct the study, you've chosen your site using the guidance from the design chapter, you know which chemicals you're going to use, you're making decisions about online instrumentation and the sampling plan, you can use the advanced tab and get a more specific estimate of cost for the pipe rig study. So for example, looking at the screenshot on the right from the advanced input screen, you can see that we can now enter in the harvested pipe material segments versus new pipe materials. You can say whether or not the pipes are harvested during lead service line replacement because that impacts the costs. There is a cost to, even if you're already going out to harvest the pipes or to replace them, you need to do it in a very careful way to preserve the pipe scales, and that's captured in some of the videos that were mentioned earlier. We have different costs for each, and then you can enter in the chemicals. That kind of helps with planning, and the flow period that's going to affect the quantity of chemical needed, and along with the flow rate. And then you can enter in things for the test facilities, like do you already have a temperature controlled space available for testing? And then the last thing I want to highlight is that for the advanced tab, you can actually enter in your sampling plan and get pretty accurate analytical costs. And you can use this as a tool to think through your sampling plan, and also to, if you're thinking about trying to trim analytical costs, places where maybe you can back off on the frequency and the impact on the overall analytical feed. So with that, I'm going to pass it over to Dave to wrap up.
Hey, thanks everybody, and thanks for listening. We're going to move into the question and answers here in just a minute. Just to highlight a few of the things that are key to our, there's so many things key, but a few key things. I hope you picked up that clearly defining the study drivers is critical to success. An old friend of mine always said, you have to know the question you're asking or you won't find the answer. So figure out, certainly up front, what it is you want to try to figure out, lay out a study that will get you there, and the data collection that will get you there. when you get done. A clear understanding of influence factors is needed for proper siting, design, and operations in order to meet your objective. Design the rigs carefully. You've heard that from Pierre, that yes, there's lots of different options, but make sure your flow can be balanced and monitored correctly. The only way you can know if you have leaks, et cetera, that was on one of Pierre's slides, is if the loads are closely monitored. We like to use a flow totalizer to compare to the individual flows, so we have double checks. Sample taps are horizontal or below the pipes to capture all the lead. Air can be released from the system, and pipe flows and sample tap flows represent the system, as Rebecca talked about. Carefully develop a data collection plan. It's too late when you're done. Say, oh, I forgot to get that kind of data and I needed it. Well, you don't want to start this thing over again. So really think about that. That gets back to the questions I'm trying to answer. What kind of water quality parameters do I want? Do I want them to be flowing or stagnant? How often am I going to collect lead? And those kind of questions. Pre-plan the questions to be answered. We mentioned about that to get your objectives. Statistical tools for stability and CC differences are important to supplement graphics. I know lots of us don't like to play with statistics, but there's some very good instructions and some use of R in the manual to be able to do that. And then finally, the costs vary depending on site-specific factors, but can be significant. I've seen many of these systems jump up into the 7 figures. So don't underestimate the cost, plan ahead, and don't underestimate the time it's going to take. You've seen some of those time factors, 18 to 24 months, not being uncommon at all for the time that needs to be taken place. So Jan, I'm going to turn it over to you for question and answers, and thank you.
All right, thank you all for the excellent presentations. We have many questions already come in, but before the Q&A, I would also like to thank the PAC, the Project Advisory Committee. We always have a PAC, that's a group of volunteers for each project to ensure the technical progress of the project. So for this project, we have Steve Via from AWWA, Daniel Williams from EPA, Hua Jiang from City of Tulsa, Manju Inyang from Massachusetts Water Resource Authority, and Kurian Mulwick from AECON, Canada, and Andrew Kirata from Copper Development Association, who volunteered and contributed to the PAC. So now, thank you so much for your volunteering work. And now let's get to the Q&A. I think the first question will be for you, Dave. What are some concerns about conducting pipe rig studies at the treatment plant versus within the distribution systems?
Okay, thanks, Jan. That's whoever that was. That's a good question. Certainly, most of these are done at the water treatment plant, but what you want to make sure you do is look at the difference in your water quality, key water quality parameters at the plant and in the distribution system, right? And because often at the water plant, you have much different conditions than in the system. A simple case might be I'm going to use orthophosphate and my water plant pH is 7.8. In the distribution system, it's 7.4. Say, hey, that's all in the right range. If that's the only thing I see different, I can do it all at the water plant. On the other hand, I might be trying to test at the water plant to see how well a pH of 8.7 works, where I might start to form a pretty low soluble hydrocerocyte. But out in the distribution system, my plant pH is 8.3. I'm not going to form the same compound. So then I might need to adjust and go out to the distribution system. So compare your water plants. I'll give you one classical example we don't think about, which is our plant is a free chlorine plant. So at the plant, I've got a very good chance over these 18 months of forming a lead-4 scale, which is a very low solubility scale. Out in the distribution system, I might not have chlorine levels that are going to form lead-4 everywhere. And so my whole plant results have been biased, if you will, towards a compound that doesn't form in the distribution system. So look at all your water quality parameters, and that'll help you decide where you need to set these up.
All right, thank you. The next question is about acclimation, I think, Rebecca. So the question is, if pipes only settle down after a period of higher flow, would that reflect physical slowing of existing pipe scale? I'm just curious if dislodging existing scale takes away the benefit of using excavated pipes to represent historical scales and how those might react to water quality changes?
That's a great question. I think it was referring to my comment about potentially using flushing to help settle pipes down and get to stabilization. So first off, sometimes pipes will settle down on their own. In many cases, we do see that, but in some cases we don't. We see continued variability and lots of high spikes and disturbance at high variable levels. And that's after even several months, we want to try to get those to settle down, as Michael talked about the importance of that before moving to the testing phase. So in terms of the actual flow rates, a couple of things I want to point out. First off, these higher flow rates are not untypical. They are representative of flows that happen in the service line or internal piping. When you turn on a bath, for instance, you have a much higher flow rate within that service line. So we're talking about typically moving from 1.5 gallons per minute to a 2 or 3 gallon per minute flow rate. We obviously want to check velocities and make sure that we're not exceeding 3 feet per second. So these are very representative of typical regular flow rates that happen through those service lines. I also want to mention that we're not trying to scour the scale. We're trying to just dislodge particles that may have been trapped anywhere within the piping, including the sample taps or valves. When we harvest these lines and install them on lines, it's often that we get those particles trapped in the actual pipe rig, and then they're just being, they're coming off in the samples periodically. So if we do that, occasionally we can get some of those trapped particles out of the system. That's not impacting the overall results of the study. Great question.
I think the next question is a cost, regarding cost. So Caroline, how did the calculated cost using the model compare to the real cost for these participating utilities?
That's a great question. And so what we did kind of as a quality control check is we used 2 different case studies that were had different characteristics, and we entered in the criteria for those case studies into the tool after it was developed, and we compared the cost to the cost that was developed from the model, and made a few tweaks where it made sense that the costs weren't coming out as we would expect, and then got it to a point where across kind of the range of different test conditions that you might have, it was a pretty good estimate. So it is important to note this is a conceptual level cost tool, so it's not going to be an exact cost, but and where we felt like it was appropriate, we tended on making sure we're conservative, because you don't want to think your pipe rig is going to cost $200,000 and then it ends up costing $400,000. With the participating utilities, the case study examples, and all of the individual unit costs, it's a good starting point to be able to budget plan for these studies.
Thanks. So next question is, how much impact does seasonal water temperature variation have on pipe loop results? So in a geographical area that with hot summers and cold winters, do you need to run the acclimated loops for at least a year? Or could there be ways to represent the worst case in a shorter time frame? Melinda, you want to take this?
Sure. We definitely would recommend running these rigs for a year to capture seasonal variation. And this can be especially important in surface water treatment plants, where we see much more variation than in a groundwater plant in terms of temperature. But there are also seasonal operations, chemical dosages that may change seasonally that can impact corrosion control. In terms of worst case, that can be difficult. We have to remember that the metals that we're concerned about can be in different locations within the premise. So, service lines that are outside of the building may be subjected to some of those temperature fluctuations. But if it's lead, copper, solder, brass that's at a fixture that's in a kitchen, that's at room temperature most of the time, and the water's stagnant in there, may be at a very different temperature than what's coming out of the treatment plant. So there's no easy answer to that. Warmer water certainly will enhance the corrosion and metal release reactions, but we do recommend a full year of seasonal operations to capture temperature and chemical variation that may occur over a year.
Great, thank you. The next question. So the major concerns of these pipe rig studies are time and cost. So any thoughts on how much more benefit a system would get from a pipe rig study versus a desktop study? Anyone want to take?
I can make a cut, and then Rebecca, well, everybody can jump in, because that's a big question. To be a simple answer is they're two different animals. A desktop study, we always say, is a prelude to a demonstration study, right? The desktop study is designed to really tell you what your existing water conditions are, what your existing chemistry is, what your existing lead levels are in a documented kind of set, defining what your existing CCT is. And then the desktop study will give you some ideas as to what other things need to be done. The key question, other than if the regulation requires you to, like under LCRR, and you have to do one of these studies, the key question from a scientific standpoint would be, are my scales likely to be upset by this change? And that has to be assessed during your desktop study. And depending on those conditions, and that means you would probably, if you really want to dig into it, you would need a scale analysis study. And then you can start asking those questions of, okay, based on the scales I have, based on the change I'm going to make, is there a likelihood of upsetting these scales? And if you're going to upset the scales, then that moves you into a pipe rig study. The other thing I will say is there's some very good information on this in 5223, which is another WRF project. I forget the title, Jan, but it really tries to help you lead down when do you need what kind of a study. And that will help you give some of this guidance. And most of it centers in on scale analysis type of issues. 5032, Rebecca's helping me. That was 5032, Rebecca. Thank you.
Yes,
it's one of our projects. Rebecca's helping me. So yes, 5223 is ongoing now. I'm sorry. Yeah, 5032, Jan. Yep. Rebecca, anyone want to jump in on that?
I was just going to add that other reference, 5032's got a lot of good case studies in there and thoughts on when a pipe study would be warranted or recommended.
Cool, great, thank you. Let me check the time. I think we have time for a few more questions. So this is a simple question for me to read. So is there an algorithm to kind of guess the water quality 1,000 feet down the line?
I can try to say, I think if I understand the question is, once the water's left the treatment plant and it's gone through transmission or a storage, a large storage facility, how well does that water represent, what you're seeing at the treatment plant? And no, there's not just a simple algorithm, but certainly people try to do water quality and hydraulic modeling to try to understand some of those changes. But that's where the monitoring, baseline monitoring, when you're doing your system design, you've got to understand your drivers. You've got to know how your water chemistry is changing from the point of entry, leaving the treatment plant, through storage, through the distribution system, and out closest to the premises to try to set up the study as best as possible.
So I think the next question is related to this. So what if it hits a concrete aqueduct before it hits like a regular town distribution system, I guess, whatever concrete, if it runs through concrete and not just metal?
I guess similarly, depending on how well your water is buffered and the alkalinity and the buffering capacity, you could see pH increases as it moves through cement. So it could be different out in the system than leaving the plant. That's an example Dave gave earlier.
All right. So next question, is there in any of these case studies was moving from poly or blended phosphate to 100% orthophosphate considered?
I'm not sure if that was one of our case studies. Aqua went from a polyphosphate to more conventional, but I don't think it went. I don't know if the source was from poly to ortho of that study.
That was a poly to ortho, but it was, yeah, it wasn't it was a poly to an ortho. You could say that because there was also a source water change. So it's more complicated. Yeah, it's not that simple. Yes, you're right, Melinda. It's not that simple. I'm not thinking of one. There certainly are some out there, but I'm not thinking of one offhand.
I think the one thing to add to that question is that the guidance document is meant to be informative for the whole range of types of changes that could occur in terms of treatment, sources. And so the guidance provided is applicable across those different drivers that Melinda talked about, and a switch from blended phosphate to ortho, or bringing in a source water with a different pH. The basics of design and operation and thinking through those questions are covered in the guidance document.
Thanks. I think our time is up, so I would like to thank you all for the presentations. I would also like to thank audience for the great questions. We still have several questions not answered. We will do our best to email you the answers. But otherwise, that's it for today, and everyone have a great day. Thank you so much.